Okay, so we have to find the area of the shaded region, and that shaded region is just a trapezoid. So algebraically or geometrically, this is a pretty quick problem. There's a reason why we're doing this specific problem. So we know that 1/2 base 1 plus base 2 times the height, that's the area of the trapezoid, right? And in this case, the trapezoid is always the parallel sides. So what is base 1? Well, base 1 is the value when x is equal to 2, right? So base 1 is equal to 4 because that is the length of this segment. And then base 2 is the value when x is equal to 4, which in this case is the output at 5. And then the height is always the distance between the x values. So 4 minus 2 gives me the height of 2, right? Now, hopefully, you're thinking, we kind of already did this, right? We did this with different data points and we had a lot more trapezoids, but there's a reason why we're doing this today. So here's what I think of. This half and this 2, they're going to reduce out. So all that's left is 4 plus 5, and the area around the curve is equal to 9. But that's not the reason why we did this problem. The reason why we did this problem is so you guys can connect with the fact that the area underneath the curve is actually represented by the integral. And what is the integral? There's 3 parts to it, right? There's a lower limit, there's an upper limit, and those are your x values, right? Where did I go? I took the area when x was 2 all the way to x was 4, and I found the area between that. And then how do we find the height, right? Well, the height is actually the function itself, f of x. So I could write f of x here, or I could write the equation that f of x is equal to. And then we always put dx. Now, we didn't really talk about this dx yet. That's going to come up, and we'll explain why today. Why do we have to put dx there? What does it mean? Well, let's kind of look back at this and just kind of think of it for a second. And I'm going to try to color coordinate this, which means I'll put dx in a different color. Let's use purple. Now, what does the green part give us? Well, the green part is actually the base and the height. Or, excuse me, the base 1 and base 2, right? So I might change the colors on this so you can see where these come from. So 4 plus 5. Well, the 4 and the 5 came from plugging in 2, right? Half of 2 is 1, plus 3 is 4. Half of 4 is 2, plus 3 is 5. And then what does the dx represent? The dx is the change in the x's. So our height is actually the dx in this case. And just to color coordinate that. So there is a very strong connection here as to how the integral relates to the area under the curve. And our job today is to make a strong connection to that, and then also show you there's a shortcut. We don't have to graph it. We no longer have to do rectangles or trapezoids to approximate. Now, notice I put a hard equal sign here, and the reason why is there is no over or under estimation here. It's a perfect area because this line was linear. Whenever you have a linear line, you'll be able to use the area of a rectangle or a trapezoid to find the distance between that curve and the x-axis. We've got a couple slides that I'm going to go through here that I don't want you to write. We're just setting the stage for what comes up next. All right, so what have we done so far in this new unit? We talked about area underneath the curve, and we used rectangles. And we said, you know what, there were spots where we had an overestimate, and there are spots where underestimates occur. And depending on if a function is increasing or decreasing, and it's rectangles, we can tell without even looking at a graph if that's going to be an over or an underestimate. But the big idea is if I want to take a function f, and it's defined on a non-negative interval from a to b, the area under the curve is actually represented by the integral from a to b, and then we usually have f of x dx, and that is approximately. Now notice I use the approximate symbol here, and the reason why is you can see that this curve, currently, we don't know how to find the exact area, so there's over or under estimates. Okay, so that's an approximation of the area under the curve. Well, today we're going to make the link, and you're going to be able to solve that. Okay, but prior to that, all we could do was create rectangles or trapezoids. And we did talk about, if I have a region here and I had two rectangles, then that error in this case is an underestimation, but the error is quite large. So what could we do to reduce that error? Well, one of the things we saw is the more rectangles we take, the smaller that error becomes. So if I took 4 or 8 rectangles, you can see the error is getting smaller and smaller, which gets us to a more accurate representation of the total area. So the question would be, how many rectangles would I need to make this a perfect model for the area under the curve? And it's not 2, it's not 4, it's not 8. It's actually an infinite amount. So if I had an infinite amount of rectangles, that would make this error so small that eventually the error would be 0, and we would get the true answer of the area under the curve. However, that's not practical, right? We're not going to find the area of an infinite amount of rectangles. So what's the connection? And that leads us to the definite integral. So could you please write this here today? This is going to be the start of section 6.3, day 1. We're going to spend 2 days on this, but today is the big day that connects everything we've been doing together. And the good news is that if you were struggling with antiderivatives, okay, if antiderivatives were not going great, you're going to get a ton of practice with them. And one of the things you might have noticed is from us doing antiderivatives, we're reversing the derivative process. You're learning derivatives again just backwards. So we are reviewing a lot of the things we talked about from first trimester. So I hope that you can see that we keep cycling back on these major concepts in calculus, which means if you don't understand it yet, there is a chance where you could learn it in a different way, and that could still form more knowledge for you. So my hope for you is that you never give up. Keep on trying, keep on working at it. Some things are really hard, some things aren't as difficult, and calculus is kind of like a roller coaster. Okay, so just a quick sketch. If I had a blue function here, f of x, that isn't a linear model or anything made up of straight, friendly lines, I couldn't really use geometry to find the area under this curve. So what could I do? Well, this is where the definite integral comes in. And the reason why we use the word definite is because we have specific bounds that go in there. In this case, we go from A to B. All right, if it was indefinite, we'll talk about those in section 6.4. That just represents more of a process than the area under the curve. So the signed area between any curve on the x-axis and on the interval. Now, here's the part that I don't know if you really want to write down. I just kind of have to mention this, and I'll just state we did not do anything with summation notation right now. You've talked about summation notation in sequences. You did that in Algebra 2, and I believe a little bit in pre-calculus. But let me just show you what all this means, okay? Because it could be kind of confusing. We have the limit as n goes to infinity, and then we're going to take the summation symbol. Okay, this is sigma, and this stands for summation. It means add up all of the outputs times the change in the x. Well, we talked about the outputs being the height, right? The output of A would have a height, the output of B would have a height, and if I had a rectangle drawn in here, right or left bound, it doesn't matter, right? If I had a bunch of these rectangles, the height times the width, this is just the area of the rectangle. right? Area of a rectangle is represented by height times width. Well, this notation leads us into a better, more friendly notation called the integral. And why does n go into infinity? Well, what does n mean? N is the amount of rectangles. So if I have one rectangle, that's where we'd start at 1, and then I would go to 2, dot, 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 and I would go all the way to whatever n is, right? N number of rectangles. Well, we want n to be an infinite amount. So I would just have an infinite amount of rectangles all added up, and that would model the perfect area under this curve. So the change in the outputs is the height. dx, this is another way to say change in x is dx. And another way to say f of c is a function f of x. So really, this whole notation says we're going to find the area under the curve from a to b of the function with respect to x, the change in x's. So f of x is my outputs, that's my height, and then dx is the change in the widths. So really, I look at this as height times width. Okay. So don't get super confused. We are not going to deal with the summation notation. There may be one multiple choice on the actual AP test about this, but I have found that it's not worth our time to learn it. And in that case, if you see a symbol like this and you don't really understand it, take a guess on that specific question. In the long run, one problem on an AP test is not going to make or break you at all. So now we are going to talk about some quick properties here and just have you guys understand what we're looking at. So what if I gave you the integral from a to a of f of x dx? Think of that graphically right now. And I want you to send in the chat, send me a private chat. What do you think going from a to a f of x dx, knowing what we know about this symbol and what it means, what do you think the answer is here? Send me a private chat. If you don't know, you can put IDK. That's fine. I just want to know you're paying attention. So these are just two properties that we're going to kind of explore. We're going to spend a lot more time learning different properties about integrals. The nice thing is, integrals is the inverse process of taking a derivative. So the properties for derivative also hold true for integrals. So the one where we have flipping the bounds, that one wasn't super present on the derivative side, but this is kind of the newer one. Okay. So the first part, I have a couple of problems that this is very similar to your Delta Math homework. I don't want you to write this down. We're going to do a couple of them where I just want you to see the process, and it's super quick. So what do we have? The regions A, B, C, and D in the figure below are bounded by the graph of the function in the x-axis. That's important to note. So when we say it's bounded, that means region A is bounded here and it's below the x-axis. So we'll talk about that. And then bound region B is the region above. And I'll shade those in so you can get a more visual. And then they tell us we know the area. Now, when they tell me the area, that's just the amount of space that is taken up. Okay, so like region A here is 6, but if you notice, if I did the difference of the x's and then the height is actually below the x-axis, so that is going to actually end up being an area of -6. Okay, so that's what we got to think of. If it's below the x-axis, it's a negative area, which would mean B, region B, is 10. So then this region right here above the x-axis would be a positive 10 because we're up above, my output is positive. And then I'll just kind of fill these in. I'll put the numbers next to them. Region C then is 8. Now notice, we don't know, we couldn't calculate these exact areas because we don't know the function, and it's not a nice model, so they have to give us what the value of for each one is. And then region D is 17. So now they can ask me a ton of questions from a problem like this. So what I would do if I was, let's say this was a test question and I could write on the test, I would go and just say, okay, well, what is region B? Region B is a positive 10 because it's above the x-axis. Region D is a positive 17 because it's above the x-axis. And region 8 is below, or region C is below, so it's a negative 8. Well, what do they want us to do now? They want us to find the area under the curve. Now, what is the curve? The curve is f of x from x equals negative 4 to x equals 8. That's what the integral means. Now, let's say that this was an AP problem and you had to write it by hand, which this wouldn't be a free response question. What you should do is we're going to learn the properties here, okay? And what I want you to focus on today is I know getting the answer could be very quickly. I'm not really concerned about getting the right answer. I'm concerned about setting up the correct notation. So what do they want me to do? They want me to start at negative 4, right here, and then they want me to go all the way to 8. Well, if I do that, I'm adding 1, 2, 3 different areas together. So what I'm going to actually do is I'm going to set this up, and one of the properties of integrals is you can actually go from the first integral, which was above the x-axis, from negative 4 to 0 of f of x dx, plus, then the next interval would be from 0 to 3 of the same function, f of x dx, because that's what this curve is, plus the last value that went from 3 to 8. Now, I understand, again, I'm not super concerned about the answer, but we know each one of these. They didn't tell me that specifically, but I know the area under the curve from negative 4 to 0 is positive 10. And then I know the area under the curve from 0 to 3 is negative 8. And then I know the last one, the area under the curve from 3 to 8 is a plus 17. And then you can add all that up, and we get 19, I believe. Okay? So please, please, please don't just think of adding these up. Think of how the integral is broken down, because this is a very important property that you can represent the area under a curve from negative 4 to 8 as the sum of each individual piece. And you'll notice where are the intervals? It's at the zeros, right? And I still cover the same ground. I go from negative 4 to 0, and then 0 to 3, and then 3 to 8. So I still cover all the area from negative 4 to 8. Okay? And that is the area under the curve is 19. All right. I don't want you to write this one. I'm going to have you do one after this. So what if they don't give me the values under the curve and they just give me a function? Now, first thing I want you to notice is this function is made up of straight lines and a semicircle. So that means the area under the curve can be geometric, which we can use our algebra or our geometry problems for this. So the function f is shown below. It's made up of a semicircle and piecewise linear segments. Find the value of the integral from negative 4 to 3 of f of x dx. So you need to think of, I got to find the area underneath the curve. Now the very first thing is when I say underneath, we're talking about the area between the function and the x-axis. And that is one of the mistakes kids make, especially if they were given a graph like this. So it's very important to understand what this means. Area between f of x and the x-axis from x equals -4 to x equals 3. So let's look at that. Where is -4? Here it is. Here's the x-axis. So I need the area underneath this curve from the x-axis all the way to 3. So I got to find this area. Now, as we learned, we can break this up, right? I can break it up into some familiar pieces, and the first area is pretty friendly. That's just a rectangle. Now, if you're given a graph like this, most of the times you should know automatically, is your answer positive or negative? And since we are completely underneath the x-axis, I know that this answer will be completely negative because this area is all negative. So watch how we set this up. If I'm going to find the area under the curve, all right, of the entire thing, we're going to break that down into the things that we know. We know I can find the area from -4 to -1 very quickly because that's a rectangle. So let's do that part, and then we'll find the area underneath the curve from -1 to 3. That takes a little bit more creative thought to find that area. But let's look at the height here. How tall is this? Well, we're going to count 1, 2, 3, 4, 5, 6. And then here we got 1, 2, 3. Now notice I'm going to call this a -6 because it's going down. So the area of this function is the f of x part is the output, that's -6. The dx is the change in the y value. So that's kind of like thinking height times width, right? But I know that that part is -18. Okay, let's see it. But how do I do the area of this part here? This is a little bit tricky. So what we have to do is you have to realize, well, wait a minute. Geometrically speaking, the area of this part is actually the rectangle minus 1/4. Ooh, then that's a quarter circle, right? Because if I took the area under this curve right here, I'm basically subtracting 1/4 of this circle. So I'm going to take the fact that this is a 1, 2, 3, 4 rectangle. We already know the height is -6. So the area of this rectangle, if it was completely shaded in, would be -6 times 4. And then I'm going to subtract 1/4, so 1/4 pi r squared. So 1/4 represents the quarter of the circle, and what's the radius? Well, the radius is 1, 2, 3, 4. So I'm going to plug 4 in right here. And then if I multiply this out, 4 squared is 16. 16 times 1/4 is 4. So this actually will be a -4 pi. And then I'm subtracting it because the reason why it's negative is because it's below. But then I would be taking it away from the -24. So what I would do here then is this area is the rectangle. And I know it looks like we're saying plus. Okay, somebody asked a good question. How do we know this is a quarter of a circle? So notice right here, it tells us that this big shape is a semicircle, and I'm taking exactly half of that. So therefore, this would have to be 1/4 of a circle. So now I'm taking the area of the red part plus this piece here, which we don't have a great way to do this, and it says write your answer in simplest form. So I would have to take -18 and add that together. So that's, I think it's -52, 42. -42 plus 4 pi. And that would represent the area of the shaded region here. Now, it's a little trickier when you have your semicircle below the x-axis and you have to kind of find the area here. If we were just finding the area under this circle, it would just be the 1/4. So what I'd like you to try is I'd like you to, oh, we got rid of that one. But you'll have homework problems like this on the Delta Math. They go through examples. You can watch their video if you need more help. How did we get 4 pi again? Well, this right here, I didn't set this up, but we know that pi r squared is the area of a full circle, right? So if this was a full circle, it'd be pi r squared, but we want 1/4 of that right here. And the radius goes from this, where the center of the circle would be, out to any edge. So I would just count the radius as 4. So I didn't show all of my work there, but 4 squared is 16, and 1/4 times 16 is 4, and then we just leave pi. So that's the area of the quarter circle, and that's what went right here. And like I said, there's more examples like this on Delta Math if you need them. I actually don't want you to write this part either, and I understand that we are going to have a lot to write today coming up. So this is just setting the stage. So let's think about this really quick. If I give you an interval from 1 to 3, so you know what your bounds are, and you could graph this, right? The question is what is the function here? So notice 4 is the function f of x. It's just a straight line. 1, 2, 3, 4. So we could do this graphically, right? I want to find the area underneath the curve, and here's the function f of x. Right? F of x is equal to 4. That's just a straight line. So if I asked you to go from 1 to 3, well, what you would do is go 1, 2, 3, and you would just find the area, right? Nothing crazy. What is the area of that? Well, from 3 to 1, that is the change in your x's. So you can think of dx is 2. And what's your output? Right? The output is the height, and that height is 4, which, notice, that's what that is. Now, the area under the curve is 8. Okay, so what if I ask you to do from 1 to -4? Now here's where you have to be careful. Notice, look at the bounds. We always want the smallest one to be on the bottom. In this case, -4 is up top. So what I'm going to do first is I'm going to apply that property that I learned, because we always want to calculate area from left to right, almost like you're reading a sentence. So what I'm going to do first is I'm going to put -4 to 1 of 4 dx. However, what did I do? I flipped the bound, so I have to compensate for that and make it negative. And that was the one property that we just introduced on the last slide or two. Well, now this is nothing new or different. We're finding the area from 1, 2, 3, 4, from -4 to 1. right? And that's nothing crazy. What is the dx, the change in x? Well, you could count 1, 2, 3, 4, 5, or you could do 1 minus -4 and still get 5. But dx is 5. Now notice, because this is a linear function, the height of this rectangle is still 4. So my answer here would be 4 times 5, which is 20. Now, we technically also know that I know the area from -4 to 3, right? I can do that without doing any extra work because what is it? It's the interval from -4 to 1 and then from 1 to 3. So it's these two pieces added together. It's the 20 that we had from before. It's the 8 that we had in the first one. And then our answer would be 28. And there is a reason why we're doing all this. So I know you're thinking, Strap, we're just doing geometry right now. Well, you're mostly true. Let me show you another one here. And this is the important piece. We're kind of using building blocks in terms of how we're going to set things up. So, actually, you know what? I don't want to do that. I want to keep that just in case. What if I go from 1 to A, right? Now, A, we don't know where A is going to stop. I just know A is probably going to be larger. So what I'll do is draw a rough sketch here. And let's say I go from 1 to some random spot A, and then we're at 4. So I don't need a super detailed graph, but I know that here's f of x, and I know I'm going to start at 1, and I know I'm going to go to 4. I know the height is 4, but what is the dx? Well, the dx is the upper bound minus the lower bound, right? It's the change in your x values. So how could I write this? Well, area is the height times the width. Now, just really quick, what if I distributed that and I got 4a minus 4? Okay. That actually, there's a connection here. And I want you, maybe you see it, maybe you don't, but there's a connection between the function itself and 4 minus a. Okay. Oh, Jonathan, thank you for that. I missed one small thing, which it ends up being a big thing. Notice how I had to flip the bounds? This should be, because I went the opposite direction, I went negative. Right? Because these bounds were originally flipped, this is negative, which means I was calculating this area from right to left. So this should be negative. Now that actually does not change this answer up here, because this one, this interval said start on the left at -4 and go all the way to the right. So this answer is 20 plus 8 is 28. But because they wanted the bounds flipped, that's what made this negative. It doesn't change the amount of space it takes up. It's just the direction that we calculated in it. So thank you, Jonathan, for catching that right here. Okay. There is a very strong connection between I started at 4 and what did 4 turn into? All right. Now, one of the things we'll develop on the next slide is that specific piece. Okay. Let's talk about this one really quick. And I don't want you to write this either. All right. We're just developing, and that's part of what we need. If you do ever want to go back and look at these notes, you can. But once we develop this little shortcut, you're never going to have to do this area piece for problems like this again. So let's take a look at how we got the answer of 8 and where 8 comes from. So I've got the function, right? That's my function f of x. which is just a linear equation that says, okay, your y-intercept is 2, and then go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. So there's my function. And it is always important to kind of label it f of x. Okay. Now, what if I asked you to find the area from 0 to 2? Okay. Here's 0, and here's 2. What kind of shape do I have? Got a trapezoid. And what is base? So it's 1/2 base 1 plus base 2. Well, base 1 is 2. Base 2 is 1, 2, 3, 4, 5, 6. And then what is the dx? The dx is the change in the x's. So that's officially 2 minus 0, or the top bound minus the lower bound, which is 2. Well, now there is an important connection here between 2x and 8, and we'll get there in a second. But what if, I'm going to erase this so we can see the pattern develop. What if I told you to go from 0 to x? Okay, so we know where 0 is. That's the first part here. But what if I just picked some random x right here? Well, if I go over x and up its output, this is at the point x comma f of x. So let's do this. Is still a trapezoid, right? If I shaded this whole green area in, it's still 1/2 base 1 is still 2. Base 2 is the height. Well, what is the height? It's the y value. So we're going to call that f of x. But wait a minute, don't I know what f of x is? And then we would multiply by the change in, so what is the change in the x's? All that is the upper bound minus the lower bound. So I'm going to put x minus 0. Okay. And instead of putting f of x, I'm going to put what f of x is equal to. Right? So f of x is the function 2x plus 2. Now, we can algebraically clean this up, right? If I don't care how you do it, if you want to add the like terms first, or if you want to just times by 1/2 to all of these pieces. Right? So if I do that, I get 1, I get 1x, and I get 1. So if I add those together, that's 2 plus 1x. And then, don't forget about this x minus 0, or I have an extra x out here. So if I distribute the x, I get 2x plus x squared, or I could rewrite that as x squared plus 2x. Okay. Now, I'm not super concerned about all of this. What I want you to look at is this is the algebraic simplification of the integral. Wait a minute, isn't there a connection? Do you see a connection between f of x and what the answer would be? Okay. Now, I think developing this really leads us into seeing what's going on. So what if I took the same value, but this time I started at 3 instead of 0? What would that look like? So now if I start at 3, where let's do a different color. Here's 1, 2, 3. I'm going to start at 3. And I know that when x is 3, it's output. Now, instead of counting, I could just plug 3 in here, right? What is 3 times 2? Well, 3 times 2 is 6 plus 2. This output is 8. So if I find the area under the curve, base 1 is 8. right? And then I go to some random x. Maybe that x is the same x as here. Maybe it's a really skinny trapezoid. That's fine. But what happens when I plug x in? What is its output? It's 2x plus 2 again. And then now, what is the dx? The dx is the difference between x and 3. So I would do x minus 3. And then we just want to algebraically simplify. So I'm going to do part of this in my head. 2 plus 8 is 10. And then if I cut that in half, I get 5 plus, and if I cut x in half, I get x. So I just simplified this, and then I cut it in half. And then I'm going to multiply by negative 3. I'm going to do the x's first because I just want this to be in a nice order. So I get x times x, and then I get a x times 5, so I get a 5x, and a negative 3x, which is a positive 2x, and then I get 5 times negative 3, which is negative 15. Now, you could show more work, but what I really want to do is I want you to look at the function itself and look at my answer. You see a connection. Okay? And if you don't, let's try one more. Just so we can kind of really solidify what this looks like. Okay, so now I'm going to start at negative 1, which is right here. Well, notice that output is 0, right? So I get 1/2, the output is 0. And then let's say that we use this same x right here in green. Well, what is the output of x? It's 2x plus 2. And then dx, what is the dx? Dx is the difference between your upper bound and your lower bound, or it's the difference between negative 1 and x, which is negative 1. You're subtracting x minus negative 1, which actually ends up being a plus 1. All right, so that's the area of this. Technically, it's a triangle, but we could call it a trapezoid with a base of 0. It's the same thing. So now I'm just going to distribute the 1/2. And then if I multiply this out, I get an x squared. I get a 2x plus 1. Well, wait a minute. Let's take a look. F of x evaluated at these bounds now turns into x squared plus 2x plus 1. Well, wait a minute. Let's look at all our answers. They're almost the same. What's the only thing that they change by? They only change by a constant, which means there is a faster way to solve this. And it all connects back to the antiderivative. Okay? So what you might not see is we just set up something called the fundamental theorem of calculus. And I would like you to write this part right here. We'll explain how this is set up as we go. So this is the big idea. It's called the fundamental theorem of calculus, which means everything else that we're doing for this entire year is based off of this theorem. So if I have an integral from a to b of f of x dx, and what happens then is what did this function turn into? We took the antiderivative of this function to evaluate. Okay, so notice f of x, the lowercase f of x turned into capital F of x. And then if you're noticing, we really just evaluated the bound at b and a. That's your change in your outputs. So this is the big piece today. What do we do? What's a better way to solve all these pieces without creating an area graph? Well, we can evaluate the antiderivative at b. Right? I just plug b into the antiderivative, and I'm going to subtract that from A, the antiderivative evaluated at A. And we're going to do these together. So this is one of the things that I'd like you to really take note on how we show our work and all the steps that we do, because we want to kind of show proper notation when we're using this. All right. Notice how they call this the definite integral. Why is it the word definite? Because it's between 1 and 2. Now, you could graph this if you wanted to. We're looking for the area under the curve from 1 to 2 of this function f of x. Well, what I need to do is I need to find the antiderivative. And here's how I do it. We're going to do each piece at a time. This is 12x to the third. Well, if I'm undoing the derivative, I'm going to add 1 up top, so I know I'll get a x to the fourth. But this 12, if I put a 4 up top, I have to compensate for that, and I've got to divide by 4. Now, some people like to write it like this, so they just write 12x to the fourth, and then if I put a 4 up top, I've got to divide by 4 there. And that will compensate it. I'll simplify on my next round. Or some people like to do it here, and they see that 12 over 4, this is really going to turn into a 3. Okay. So actually, I might write this, put a little space here. But that's what this should simplify. Now, if I'm not sure on this answer, I can take the derivative of it and go back to where I started. Is the derivative of 3x to the fourth, does that give me 12x to the third? Yes, that gives me the original value, right? The 4 comes down, times by the 3, and we took 1 away, so I get 12x to the third. Well, right here, we got to do the same thing. This is 2x, so I got to add 1 to the exponent. Since there's already a 1 there, this would be 2x squared, and then I'm putting a 2 up top. If I put a 2 up top, I have to compensate for that 2. So I'm going to put a 2 on bottom as well. And that part, the 2's would reduce out, and I'm left with x squared. Now, that's just the antiderivative, right? That's basically that's what this is. I didn't do anything with the bounds, but I used this integral symbol. The integral symbol is finding the derivative. Okay? Now, what I have to do is I still have my bounds present, but the integral, we're just going to turn that into a straight line, which means evaluate. Okay, so technically you could skip this middle piece here and just take this and jump right from here. But I need to see this part right here, because that tells me what your antiderivative is. Now's the tricky spot. So, great question. Jonathan, you're on the ball today. He says, what about the C value? Well, in this case, you'll see here in a second, but because we know specifically that we're finding the area between 1 and 2, our C value will be present when we're all done. All right, so what are we going to do? Now, try to color coordinate this if you can. We're going to take the top bound and plug that in. Right? So watch what happens. I'm going to take the original, now I'm going to take the antiderivative and I'm going to evaluate it at the top. And here's the part that a lot of students end up screwing up. We're going to do the top minus the function evaluated at the bottom. So notice how I put parentheses around there? Because watch what happens. When I plug in 1, I get 2 functions. I get 3 times x to the 4, x to the 4th plus x squared. But we're evaluating it at 1. So I'm going to put a 1 here and here. Okay. What is this? Technically, this is the antiderivative evaluated at b, which was my upper bound, minus the antiderivative, that should be a capital F. Make that look more capitally. So see how it's f of b minus f of a? It's the antiderivative evaluated at the upper bound minus the entire antiderivative evaluated at the lower bound. Okay. Now we have to simplify carefully. Well, 2 to the 4th power is 16. 16 times 3 is 48. And actually, I think I do that here. And then plus 2 squared is 4. So that's 52. Minus, and this is 1. 1 times 3 plus 1 is 4. My answer is 48. Now, and Jonathan, I'll go back to your question. What about the plus c? Right? The plus c was for a constant that would give us a general antiderivative. Well, this is a definite. We already kind of know the points. We're using 1 and 2 to evaluate it. So what does that 48 mean? We just found that the integral from 1 to 2 under this curve is equal to 48. This is the area under the curve, 12x to the 3rd plus 2x, from x equals 1 to x equals 2. And since we know the points 1 to 2, we aren't going to have a generic plus c, and this is just the area that would be filled. So if I was to graph it and shade between this function and the x-axis, I would fill up 48 units, square units. All right, let's try another one. Now, there are some ones that are trickier, right? And eventually that's going to be the route that we're taking here, is the antiderivatives aren't all kind of friendly power rules. We know all the derivatives possible, so now we can undo them all. And that's what makes this hard or challenging, is I need to figure out what's the antiderivative of 12 over x to the 3rd. Well, before I do that problem, I really don't like this, right? That's not a friendly form, so we just need to rewrite. Notice, I'm not going to change the integral at all, but I'm going to rewrite this. I'm going to take this x to the 3rd, and we're going to move it up out of the denominator. And now, this is just undoing the power rule again. We're going to find the antiderivative. So I'm going to add 1 up top. And when I do that, negative 3 plus 1 will be a negative 2. Now, this is the way I do it. I say, okay, well, I would have a 12 here, right? But if I put a negative 2 up top, I got to divide by negative 2. So I kind of put that negative 2 here. And then 12 divided by negative 2 is negative 6. And there's my antiderivative. And then the integral symbol, this symbol is the antiderivative. So this symbol goes away when we take the antiderivative. The dx, by the way, the dx, remember that's the change in the x values? So the dx goes away when we just plug in the bounds and subtract them. That's why we have the dx there. That's like your width if we were finding the area of a trapezoid or a rectangle, or in general. So this notation to this notation is extremely important, understanding that the integral goes away when you take the antiderivative. And then maybe I should write dx in green, because this is what dx is. Dx is the difference at 2 and at 3. So what I'm going to do then is I always set this up like this in my head, right? I've got two things that I'm subtracting. I'm going to take the first one. It's always the upper bound, right? That's the capital F of, and maybe instead of B, I can put 2 and capital F of 1. So now I'm just plugging that into the function. So I'll plug 2 in. Since this only has one term, it's a pretty quick one. Blue. And then we're going to evaluate the antiderivative again. But this time, we're doing it at the lower bound. And notice, we're plugging these values in for x, because that is dx. It's the change in the x's. In the first example, we had 2 x's that we had to plug 2 in, and we had 2 x's where we had to plug 1 in. In this case, there's only 1. So just remember, anywhere you see an x, the upper bound goes into both of those, subtracted by the lower bounding going into both of those. And now it's just algebra. All of these should be no calculator questions. So I hope you're thinking, okay, well, wait a minute. What is 2 to the negative second power? Let's just deal with that negative and put it down below. So that becomes negative 6/4. And then same thing here. This becomes negative 6 over 1 squared, which ends up being negative 6 over 1. And then we're subtracting those. Well, if I'm going to subtract, I want this to be the same denominator. And I could have reduced, I guess I maybe should have, but this will work. So then I get negative 24 over 4. 6 minus negative 24 over 4. Well, that's going to turn into addition. So negative 6 plus 20 is 18, all over 4. And then divide those by 2. And the area underneath the curve is 9/2. I think it's very important that you understand this is the area under the curve. It's the area under the curve of the function 12x, 12 divided by x to the third from x equals 2 to x equals 1. Okay, we've done some of this already, a little bit, but not a lot, and we never made the true connection as to why we do the antiderivative, and that's what today was all about. So, I thought we were going to have time for this one. I'll save this one for next week. I want to show you this one. Don't write it, but look at the directions, because that's a lot of times kids see this problem and they freak out. Well, what is it? Find the area under the curve of f of x e to the x from negative 1 to 1. What's another way to ask this? Find the area under the curve from negative 1 to 1. That's my integral. What's my function? It's e to the x dx. Now watch how fast this is. What's the antiderivative of e to the x? So whose derivative gives me e to the x? That's e to the x. Because we have bounds, we don't put the plus c anymore. So now I'm going to evaluate from negative 1 to 1. And then what do we do? Well, I've got two things. I've got the upper bound minus the lower bound. It's always the upper bound. So e to the first power minus e to the negative 1. And this is e minus 1 over e. And that's as far as I can go. I mean, I could grab a calculator, but that's a number, right? That represents area under this curve. So they can creatively ask you problems to do this. Find the antiderivative, evaluate the bounds, and it's the same work. So homework tonight is Delta Math 6.3, and we're doing definite integrals and some area. So make sure when you're done with this, you submit it to Schoology, submit your screenshot. If you're struggling, please come see me in my office hours. Based off of the people who didn't do the quiz and didn't watch the video, I expect some people might be struggling. So please come see me. That's all I got. Have a good day.